So yeah, today's talk is called Code Simplicity, the 3 Flaws of Software Design, and we're going to get right into it. So the first thing is, interesting. Next. Okay, here we go. Who am I? Well, obviously I am a person. I am at mkanat on Twitter if you want to follow me, but I'm also the author of Code Simplicity, a book published by O'Reilly, and a blog by the same name. I'm the chief architect of the Bugzilla Project, the open source Bugzilla Project. I'm a software engineer at Google, and specifically I work at YouTube right now. And I have also done a lot of other things in the world of software and other things in life, and those are on my personal website, which is listed there at the bottom, max.kanat.us. So the book Code Simplicity is about a series of laws for software design. The idea is that we want to take the fundamental principles of software development and try to find what we can about that are the most basic ideas. What are the real underlying laws of software development? And in my last webcast, I gave a whirlwind overview of those laws. And now I want to sort of dive deep into one of them, and particularly a very particular aspect of one of them that I think is really important. So the law that I want to go into is called the law of change. And the law states, the longer your program exists, the more probable it is that any piece of it will have to change. Anybody who's worked on a software system for a long time has seen this. Essentially what happens is that your requirements change, or your users file a bunch of feature requests and you need to make changes that you didn't expect. And that these changes sometimes touch various different parts of the system that you couldn't have predicted were going to need to change. Now, there are various ways that software developers attempt to cope with this law, or really this sort of problem. And the problem is, I wrote a ton of software and now I have to change it, or I know I'm going to have to change it. You know, once you develop enough experience in the field of software development, you know that you're going to have to change it, and so you sort of try to plan for that in advance. You try to make your code easy to change in some way. But developers get into a couple of problems, or they make a couple of errors when they try to do this. And the major errors that they make, I call the 3 flaws. And in fact, I would say that this pretty much categorizes, as far as I'm aware, all of the errors that developers make when trying to cope with this law. This isn't all the errors that developers could possibly make about software design, which is the whole field of making decisions, technical decisions about your software. But these do cover all of the errors that people make when trying to make flexible systems or systems that can accommodate change. And so real briefly, I'm going to give an overview here of just what these 3 are, and then we're going to dive deep into each one of them individually, and I'm going to give examples of them and and how we can actually apply them to make code better. So the first one is writing code that isn't needed. The second one is not making the code easy to change. And the final one is being too generic. So let's go into each of these in more detail. The first one is writing code that isn't needed. This sounds a lot like a principle from extreme programming called YAGNI, or you ain't gonna need it. But it's actually a bit broader. So the YAGNI principle is that you shouldn't write code that you don't yet need, because you're probably not going to need it in the future. Like you're going to get to the future and then you're going to discover, oh, I wrote a bunch of code that I didn't need. Well, that doesn't always turn out to be the case. Sometimes you write code in advance and you did need it. You get to the future and it's actually useful. But what's really true is that you don't necessarily know how the code needs to be designed yet. You have only the knowledge of your present requirements. You don't necessarily know exactly what your future requirements will be. And so you can't really design a really good system for unknown requirements. So really what this principle is about is it's about good design. It's about understanding your requirements in present time and designing a system that meets those requirements in just about as perfect way as you possibly can. And in fact, I might even say that the only way to do good design is to do design for code that you actually need. That is, one of the purposes of software is to solve real problems that people have. And when you try to solve a problem that isn't yet real, your software quality suffers to that degree. And so the problems of writing code that you don't need are numerous. One of them is bit rot, which basically means that it's going to sit there and it's going to sort of, as your system changes around it, because it's not in use, it could break and you won't know about it. And hopefully it just breaks and your system stops compiling. But at the worst, it breaks and then you start using it in the future and then your users experience a bug. Another problem is that you'll probably have to redesign it when you get to the actual future, which I've basically mentioned. So you've written a bunch of code, and then you get to the future where you actually need it, and then you realize, oh, it needs to work a slightly different way, so you rework it, or you don't rework it, and you just sort of hack your system around the existing code because you already have it, which is even worse. Sometimes people think, oh, I'll just try to handle every possible thing that could happen in the future, and we're going to get into that a little bit more in another one of these flaws. But it happens here too with just writing code that isn't needed. Like, you know, I'm going to add all of the possible methods for handling strings that I could ever need right now, even though I don't need them now. And that's a mistake. And as I pointed out, it's not really saving you time because so some people say, you know, I'm going to save time by doing all of this work in advance. But you're not saving yourself time because you're actually doing work now, and then you're either going to have to throw out a significant part of that work or redo a significant part of that work when you get to the future. And finally, you're adding complexity to the system. Code, almost all code that you write adds complexity. When you add code, you pretty uniformly add complexity, and particularly when you add functionality that you don't need. You're adding complexity, and that makes your system harder to maintain. Usually we think of this as, you know, you wrote a whole class you didn't need or a whole function that you didn't need. But sometimes, and I see this even more often, as lines of code that you did not need. And I see this all the time when I'm doing code review. The rule that you can use to generally avoid this problem entirely is don't write code until you actually need it. And then when you discover that code isn't being used, remove it. You can always, you know, if you have version control, you can always go back in time and re-add that removed code if you need it later. But you don't need it now. And you can't necessarily predict that you're going to need it in the future. So don't keep it around. Just get rid of it. So what I'm going to do now is I'm going to go through an example code review where a code that just has like too much code, like, yo dog, I heard you like code, so I put some code in your code. And we're going to sort of progressively make it better. And you're going to see that it has a lot of problems, but strangely almost all of those problems go away just by applying this principle over and over and over and over. So we get this requirement. So this requirement says, I need you to parse a date string. It looks like the first half of an ISO 8601 date. It's, you know, 4 numbers for the year, 2 numbers for the month, and 2 numbers for the day with hyphens in between. And I need you to return an array with 3 integers. This is like really simple, right? The first integer is the year, the second is the month, the third is the day. This is not like code that we're shipping out to the world. This is just some convenience function that I need internally. And this example is, it's a little exaggerated. It's not totally real, but it's not that far from reality. I have seen code that looks very much like this. All right, so I'm going to share my screen, and we are going to go over this code. And this code is, I've been writing a fair bit of C# lately, so this is in C#, but I've tried to write it in a way where it should be understandable to people from most languages. So you can see that here's sort of the original mess. So I'm the code reviewer, and I'm given this. And let me just give you a second let me give everybody a second to see the screen sharing. I'll give you about 15 seconds because Catherine here is saying you guys have to do something different to see it. you should see a bunch of code, and it says the original mess at the top. Okay, we'll continue now. So you can see here he's defined some constants. He says, okay, the year is 4 characters long, and the month is 2 characters long, and the day is 2 characters long, and he's got, okay, it's a method, it takes some input, and it returns an array of integers. And now he's defining, like, okay, he's going to build up a string of the year, and okay, whatever. And he's got this comment here. He says, okay, he's going to iterate through this thing, and then he says, okay, if we're in the first 4 characters, this is the year, and then he checks, are we in the first 4 characters? And then he tries to parse each integer individually, and then he throws an exception if he gets a non-integer for each individual integer. And then he appends, so now he's building a string that's just the characters of the year. And then he's like, okay, the 5th character has to be a hyphen. We're extremely strict here. He's like, it has to be a hyphen, and if it's not a hyphen, we're going to throw an exception. And then after that, the next 2 characters have to be the month, and he's doing the same thing. He's parsing each integer individually, and he's throwing it away. And then he's appending it to the month string. So now we've got the month string. And you know, people watching this who are familiar with, you know, code development are thinking, God, there's inefficiencies here, there's, you know, over-engineering here, there's like code duplication here, and then these are all true. Like we could make all these comments, but we're going to make this code better just by showing him that he's writing code that he didn't need, and that's all we're going to do. And let me just show you the rest of what he's doing here. So he does the same thing. He checks for the hyphen again, and then he checks if, you know, if he's got the day at the end, and he does all the validation again, and then he checks if he's got more characters beyond that, then the string is too long, and he throws an exception because he likes throwing exceptions. And then he's like, oh, okay, now we've got the year string. Let's try to parse the year string. Oh, did we fail at parsing the year string? And then he's informed us of this in a comment, just in case we didn't realize that was what he was doing. And then he throws an exception. Oh, that's not a good year. And then he checks the month, and he sees, is that valid? And if it's not valid, he throws an exception. Okay. And then he tries to parse the day, and if it's not valid, he throws an exception. And then he builds the return value, and he builds it like one line at a time. He says the first element is the year, the second element is the month, the third element is the day. And he returns the return value. And, you know, this works. This works. Like if you put this into your system, most of the time it would work. It would behave strangely sometimes. You'd be like, why is it throwing all these exceptions probably? But it would work. So, but it's, you can see that it's clearly way too complicated. So let's strip out things that we don't need one at a time. And the first thing that I'm going to tell this developer that he doesn't need is not the code, it's the comments. I don't need all those comments. It is very apparent what he's doing. Even though it's ridiculous, it's apparent. So if we go through here now and we've got rid of the unnecessary comments, it takes us down to 87 lines. Originally we were at 107 lines. So we've gotten rid of quite a bit of code. And actually, and if you look through the code here now, it does actually look less complex without the comments. You know, comments are good, but they're good when appropriate. They're not good when unnecessary. They add complexity when they're unnecessary. So this is already looking simpler. But let's see what else we can do. So our next statement is, let's find out more about our requirements. What are your actual requirements? What is the actual input that you're parsing? Well, it turns out that our input that we're parsing will never, ever have a year, month, or a day that is out of range. Like our year will never be less than 0. Our month will never be more than 12 or greater than 1, or less than 1. And our day will never be a day that isn't valid for a month. And also, and this is mostly happens at the bottom here. So I'm going to go back to the bottom, right? So remember at the bottom he used to have all this extra code. And now it's become just these 3 lines, just these 3 lines. This is like how we create the year. We parse the year, we parse the month, and we parse the day. And now it's 3 lines, down from like maybe 15. Also, he was double checking the integer parsing. He had checked the integer parsing above when he checked each individual integer, and then he rechecked to make sure that that it was still an integer. But I'm sure that, I promise you that if you append integers to each other, you still have an integer. So you don't need to recheck that. So we eliminated the rechecking, and we eliminated all of the range checking because it's just not needed right now. It might be needed in the future, but it's not needed right now, and we can always add it back if we have to. And so you can see now we've gotten down to 69 lines of code, down from our original 109. Now, these are just 2 comments about things we don't need. We've gotten rid of 40 code lines, including comments. So now we tell him, in those YYYYMMDD positions, you always have integers. You actually don't need to check if you got an integer or not. So he goes, oh, okay, I can remove all of those format exceptions from the year, month, and day parsing. And now we're down to 55 lines of code. And I'll just show you. This is starting to actually look comprehensible. You can see. And then we say, guess what? Your input always has the hyphens in the hyphen position. You don't need to verify that hyphens are there. And now we're getting down to something actually quite reasonable at 41 lines of code, down from our original 109. And this almost fits on our screen now. You can see like that actually almost looks sensible. It looks a little naive. Maybe it looks like a little silly. But that's the other thing, is that when you start to remove code that you don't need, you can suddenly see the problems with the code you do need. And you can realize that you should have a simpler design. So another thing we don't need, it turns out, is we never have strings that are too long. And also, you're building that return value in 4 lines. You don't really need to do that. Like in C#, you can just define the whole array in line. So let's just do that, right? And that's part of knowing your tools, too. This is a sort of a silly example of knowing your tools. But this is where knowing your tools allows you to get rid of code that you don't need. And now the whole method actually does fit in one screen without the constants. However, if you look at it now, you can see that essentially what we've gathered of all of our requirements is that you never have invalid input. So why are you acting like you have invalid input? And our final solution is 8 lines of code down from 109. And it looks like this. It looks like, split it on hyphens, grab all the parts, and the first part is the year, the second part is the month, the third part is the day, and then return those. And you're good. So you can see that there's a lot to be gained in simplicity terms from just by saying you don't need this code. You don't need this code. There were so many other problems with that code. It had all these, it had all these extra exceptions. It had too many comments. It was unclear. But the whole problem was handled. The entire problem of complexity was handled by just getting rid of code you didn't need. And I find this very, very common when I'm doing code reviews, is developers really want to be good. They really want to, just check, just be a little extra careful. And they really don't need to. It's really simpler if you just get rid of all the code you just don't need. So let's go back to the slides here. All right. So that pretty much covers the writing code you don't need flaw. The next flaw is not making the code easy to change. And there's basically, and this is what we call rigid design traditionally. Your design is just so rigid that you can't change it. It's like you built a building out of a sheet of solid steel, and now you have to fix it. Now, how are you going to fix a sheet of solid steel? You know, that's why we have girders in buildings, because you can take them out and you can replace them and things like that, and why you build things out of components. So there's basically two ways to accomplish rigid design. One of them is to make too many assumptions about the future, and one of them is to just fail to design your system well enough. So we're going to go into each of these in more depth. Too many assumptions is the traditional big design up front or waterfall method. This is the most common way of accomplishing this. It's essentially a failure to understand that requirements will change. And one of the examples that I want to give you here to help you understand this is sort of how the requirements of the Bugzilla project changed over time. Originally, Bugzilla was a bug tracking system, and it was used only by Mozilla, and it was used only for their original browser product and a few other products. It was tracking bugs in Bugzilla itself, and the browser, and you know, some of the underlying network libraries and stuff like that. It had about 100,000 bug reports that were filed inside of it that it was tracking that you could search through. When you filed a bug, you could pick one version. Like, this is the version that I found it in, and then the developer could say, okay, this is the milestone that I want to have it fixed in, and that should be their target, their one target milestone and their one version found. And there were no custom fields because it was only used by Mozilla. So take it about, what is it now, 14 years later. Is that right? Yeah, 14 years later. And now there's somewhere around 10,000 different organizations who have Bugzilla installed. The original Bugzilla installations were entirely on Linux machines, but now Bugzilla is installed on every OS, including Windows, or just about every OS. I mean, you know, there's probably some mainframe OSs that it's not installed on, but I have had people ask me, like, can I install this on AIX? And I think there is a port that runs on AIX somewhere. So, you know, that involved an enormous shift in requirements to run in all of these environments and also to be installed by people. Like, we had to develop an entire installation system, which is actually one of the most complex parts of Bugzilla, is the installation system. One of the most common requirements that users started to develop that Bugzilla still does not handle very well to this day is that, you know, the world started to do a lot more branch development, particularly with the rise of distributed version control systems. And they wanted to say, this bug affects these 3 branches, and we plan to have it fixed in these 3 different points, and in these 3 different times for these 3 different branches. But it's all one bug. People also sometimes discovered that they had one bug that spanned multiple products. But they wanted it to be just one bug. And all of Bugzilla was sort of designed around this idea that there's only one product, and there's only one part of component in that product that this bug affects, and there's only one version that it affects, and there's only one target milestone that it can possibly be fixed in. And that's just not true in modern software development in most organizations. Some of these installations track thousands of projects, up from the original 4 or 5 that Mozilla was doing, and some of them have millions of bug reports, which is a huge change in requirements. We added an entire system so that users could add custom fields, because what was happening is people were hacking in their own custom fields. I mean, that was one of the values of being open source, was we would ship the code out to people and be like, you know, you can change it if you want. But that's a huge amount of effort for each individual organization to engage in. And even to this day, there are over 1,500 open feature requests against Bugzilla, many of which are valid. So, and most of these requirements we couldn't have predicted, and not only could we not have predicted, we couldn't have known exactly how things were going to go. However, unfortunately, the original Bugzilla code was developed in this very sort of spaghetti way. And it was designed with all of these sort of hard-coded values in it. And it was designed with all of this hard-coded logic. And it ended up taking a huge, huge amount of effort to redesign the entire system, which about 3 years, I'd say, that we spent doing the really hardcore refactoring. of the system. And from then on, there's still been a lot of refactoring, but it's just gone on steadily from there. Just to accommodate these requirements, we had to really significantly slow down development for a couple of years just to deal with these changing requirements because the system was too rigid to deal with the requirements that were definitely going to happen. So I sort of talked about that. That's sort of a huge way of doing rigid design, but you can do it in small ways too. You can do it in ways even as small as like using magic numbers or magic strings in your code instead of constants. Like this is like constants add readability. That's true. But they also allow easy change, right? Like that's one of the reasons we have constants. And this is sort of an obvious example, and it's very small, but it gives you an idea of what I'm talking about when I say don't make too many assumptions about the future. Don't assume that you're never going to need to change the value in this constant. Also, people think anytime you say we will never need to blah, that is frequently a mistake. Like people say, we will never need to have people outside of our team see this code. Somebody asked, what's a magic number? A magic number is you just type a number in the code instead of having a constant, like x is greater than 3 instead of x is greater than the named constant. So a very common one is nobody outside of our team is ever going to see this code, so we don't have to comment it in a way that, we don't have to add any documentation. We don't have to write it in a way that's comprehensible to outside. This is usually a mistake. There's a fairly good chance that somebody outside of your team is going to look at that code someday, or even if they're a new member of your team. Or people say, we're never going to need to support newer standards. Like you wrote an HTTP server and it supported HTTP 1.0 and it was fixed, and or you designed this. The worst. This is a really big problem. People are designing standards. They design standards that can never be succeeded. Like there's no like version number inside of the standard, right? There's no like you're making a protocol and you don't send along the version of that protocol. This is a common mistake. It's not made as much now, but it was made a fair bit at the beginning of the internet. I kind of wish that like SMTP, for example, the mail protocol, had version numbers in it. Or people say, we're never going to need to support international users. All of our users are in the United States, and they all speak English, and they all format their dates the same way. And they all format their numbers the same way. You're wrong. You're almost certainly wrong. There's a chance you're right, but it's more likely you're wrong. And there's lots of others of these we will never need to. These are assumptions you're making about the future, and they lead to rigid design. And the rule to avoid rigid design is that code should be designed based on what you know now, not on what you think will happen in the future. So like when you're writing a standard, now that you have this standard, so let's design it around this standard. But now that it could change. You do know that. So you allow like a version number in there or something for the standard. You don't try to guess about the future, and you don't try to you just use the data you have, and only the data you have, and always just the data you have, just your observations in present time, to do your software design. There's a bit more in the book about sort of how you can deal with the future while having that, but we're not going to go over that today. And the other way to get rigid design is to just have code without enough design, right? Like it's spaghetti code or it's slightly better. In fact, you could maybe even define spaghetti code this way. You could even say the more you assume things won't change, the more your code becomes spaghetti. Like that could even that could define spaghetti code. And spaghetti code, and just in case anybody doesn't know, I mean just code that you just write without a lot of functions or reuse or classes or any sort of organization. You just write a bunch of code in a file and you're done. Sort of the traditional way that a lot of people wrote PHP back in the day, or some very old, or some old Perl scripts look like this. And spaghetti is hard to change because there's duplication, so you've got to change things in multiple places. Spaghetti is very complex. You have to read all of the code to understand basically any piece of it. It's hard to change it safely, duplication and complexity mean that you're very likely to introduce a bug. And in fact, you could possibly also define spaghetti by the fact that it has these problems. Like you could say spaghetti code is code that has these problems. And the way that you avoid this code without enough design is that you apply this rule. The rule says the quality level of your design should be proportional to the length of future time in which your system will continue to help people. So I'm not saying that every piece of code needs to be designed perfectly. In fact, even when you have only one feature, you might be safe writing spaghetti code. But the instant you need to duplicate that code, and I'm going to go into that later, you need to make unspaghettyize it. you need to make a function or a class or something. And because you're starting to see that there's going to be a future. You're starting to see, okay, there's more to this. There's more that's coming. And that is what defines how good your design needs to be. So that pretty much covers rigid design. Now I want to go over the third flaw, which is being too generic. We also call this over-engineering. This is where you design or you build too much. Now, it is more common, particularly with more junior developers or people who have less experience, that they under-design. They do rigid designs. They write spaghetti code. They do the code without enough design problem. But it is also common for people who are really, like, they're trying to do a good job, but they do a quote-unquote good job by doing too much. They try to accommodate every possible future requirement now. And you can't. You cannot predict the future in that way. Just like I said with the changing requirements in the earlier example, you can't handle that problem by, oh, we'll just do everything now. One of the problems is that this is too much effort for the actual value that your users are getting out of it, and even that you're getting out of it. Like when you're writing a library, if you over-engineer that library and you spend weeks on it, and it really only saves you, it's only actually saving you like a couple of hours of time, then you're not getting the value out of it. You're actually sort of losing value by inputting that effort. So the sort of things that developers do to be too generic is they do things like they catch exceptions when they don't need to be caught because they think, oh, I really want to be careful about the program not crashing. And really, most of the time you'd rather fail fast because you'd rather see that the program crashed at the point where it crashed. Catching exceptions that you don't need to catch, it makes your life harder to debug. It adds code complexity. It's more code. It's code you don't need. The most common one that I see is expecting input that you never get. And you can see that there's a little bit of overlap here with writing code you don't need. Writing code you don't need is sort of a broader concept of any code that you don't need at all, whereas being too generic is a little bit more of a design thing. You think you need the code. You've decided, oh, I need this code, but you actually don't. So, this is one of the times that I see this is people expect input that they'll never get. Like you saw this in our previous example. They expected all kinds of possible inputs to their date function that they never got. And you saw how much code complexity it added. People try to handle situations that they know their code is not going to be in. Like they're an internal library that's not being used by the outside world, and they know that all of their callers are single-threaded, but they're like, just in case, let's make this thread safe. In my personal opinion, the easiest way to make a function thread safe is to put a comment at the top that says, this function is not thread safe. And to be fair, like at the points where you need to be thread safe, you need to be thread safe. But you should limit those situations, right? You should handle the situations that you know you're in. So there's also a dependency injection is very common in the Java world and in some other places. This is basically where you have a variable that creates things. So you have like a factory or something, and and instead of your class just like referencing another class, like having a value of another class, it has a factory that makes objects inside of it, so you can swap that out. Like if you want to, it's sort of like a plug-in system where you want to you have a variable, you have an object that produces objects, so that you can produce different kinds of objects. But mostly, people do this a lot when there's only one kind of object that can be produced. So just put that object there. Don't make a factory. And also people saying, oh, well, one day we might need to do this, so let's do it now. One day we might need to handle, this type of voice control input. I think there was a code review just the other day where I said, no, you're not going to need to handle that type of voice input. You're fine. And it simplified the code quite a bit. So let's give an example here. So let's say that somebody says, we're going to write an HTTP server that communicates over a TCP socket. This is your whole requirement, okay? The overzealous engineer implements it this way. He decides, well, we might want to support multiple types of sockets in the future. So let's make a system that allows for multiple types of sockets, right? So this requires 4 classes. It requires socket, which is sort of the abstract base class, and then socket type, which describes what type of socket it is, and then socket factory. So you pass the socket factory a socket type, and it returns you the socket of that type. And then, of course, our actual concrete implementation, which is TCP socket. Okay, fine. So then we're going to say, well, maybe we want to, and then overzealous engineer says, maybe we want to support protocols that aren't HTTP in the future. He says, okay, so we'll have a request, and then a request type, and then a request factory, and then the actual concrete implementation will be an HTTP request. And then we'll need responses too. So we'll have a response, and then a response type, and then a response factory, and then an HTTP response. And then also, okay, now requests, they have to communicate differently depending on, request has to know what type of response type it makes, and it has to communicate differently depending on what kind of socket type it has. So we need to make its communication system generic. And then response is going to have to understand what type of socket type it sends out on. So we're going to have to make its response, its networking code generic. And now we decide, what I'd really like to do, the overzealous engineer, what I would like to do is I would like to make it so that you can configure the socket from a file on the disk. So now we'll have a socket type reader. Okay, in our new class, and it creates a socket type that you can pass to your socket factory to get a socket. And then, but we want to support different formats for the on-disk format. We want to have a text file format, and we want to have a binary format. So we have our text file socket type reader and our binary file socket type reader. But then sometimes we want to store them on the disk, and sometimes we want to store them in a database. So we have file system config storage and database config storage, and basically we've gotten into this situation where we've got 15 classes. I would guess that this system, to get it right, is somewhere around a person-year of effort, and maybe 30,000 lines of code, because HTTP all by itself is fairly complex. And so adding all of these things on it's enormously complex. And then if you write tests, like if you want to be like a quote-unquote good software developer, which I do believe good software developers write tests, by the way. But this system, so you're going to test the system, and you've got to write tests for all of those classes. That's going to be maybe another 20K, 25K lines of code just to write those tests. Maybe not that much, but HTTP is really complicated. You're going to have a lot of test cases just for that. So what if we didn't be too generic? What if we just decided to just satisfy the requirements? There are 3 classes we need. They are socket, request, and response. And that is it. And then maybe HTTP server as the top level class, right? Which would have also been in the other one. I would guess to get this right, you're looking at maybe 2 to 3 person months. Or if you drill down more into your requirements and you say, we only need to support a subset of the HTTP specification, then you're looking at even less time and even greater simplicity. So the rule you use to avoid being too generic is to be only as generic as you know you need to be right now. how do you know that you need to be generic right now? Well, you know if you're starting to duplicate code, you need to unduplicate it. And you know that if your design is becoming complex or it's hard to keep it stable, then you need to add a little genericism in there to sort of make the logic simpler. The whole point of making things generic should be that they become simpler. And this leads us nicely into my final point beyond the three flaws, which is a method of software development that avoids them. And I'm not saying that this is the only method of software development that is valid. There are many valid methods of software development. But this is one that avoids the three flaws. And when I point it out, you're going to be like, I know what you're talking about. But let me give you a little more detail. So I call this incremental development and design. The catch here is that it's not just incremental development. So, if you just say the word incremental development, you could be like, okay, I wrote a feature. Good. Then I wrote another feature. Okay, good. Then I wrote another feature. That's great. I didn't write them all at once. That is good, and that is better than writing them all at once. But there's also an incremental design process. So the way this looks is you implement just one thing, and then every single time, at first, you implement just one thing, and then every single time you want to add something new, you redesign as much of the system as you possibly can so that it looks like the system was designed from the beginning to work exactly as it works now. And you're thinking, wow, that's a lot of refactoring. Yes, it's a lot of refactoring. It becomes less and less refactoring as you go because you evolve a system that is perfectly well suited. But ultimately, you need to get really good at refactoring. And part of that means that you need to have tests so that you can be fairly confident about your refactorings. The important thing here is that you need to have a general notion of the order in which you should build things. So you don't want to design everything up front, but you do want to have a notion of, okay, it would be simplest if I did first A and then B and then C and then D. And in general, my personal tip is that it's simplest to build these systems from the inside out. So let's say like I was building an application for YouTube, and the very first thing I did was make it play a video. Because that's the core, that's the center of the app. That's where users are getting. That's the core functionality. It's the smallest possible thing that looks like a functioning program. And then I added, an interface outside of that to get to a video. And then I added the interfaces that got you to that interface until eventually I worked my way back to the home screen. And the home screen was actually the last thing I implemented. So let me give an example of how I would do this. Let's say that we're writing, we need to implement a socket class. And we know, we have these requirements. We know that we're going to need Unix sockets, UDP sockets, and TCP sockets. Okay, what's the simplest there? Unix sockets, simplest, no question. So that's our first step because it's the simplest. First is we make a local Unix socket. We have only two classes, socket and socket test. Some of you might be thinking, but you know you're going to need to do other things in the future. Why don't you make this more abstract right now? No, because the system at every step should look like it was designed to do only what it does now. The second step is the UDP socket, because this is simpler. UDP is a little simpler than TCP. So instead, we don't want to add like a bunch of if statements into socket. We want to redesign the system. So now we have socket, which is our abstract base class, Unix socket, and UDP socket. And we have tests for each of those. We have Unix socket test and UDP socket test. And then we have a base class for the tests that shares information between them or that tests the common abstract base class called socket test. And then as our final step, we have the TCP socket. And now you see we've added a bunch of stuff in here now. So now we have socket and then Unix socket, which is a part of a socket, and then an IP socket because we have two types of IP sockets. We didn't do this before. We didn't add IP socket when we only had a UDP socket because we didn't need to abstract out all of the IP stuff. We only need to abstract out the IP stuff once we had two different types of IP sockets, UDP sockets and TCP sockets. And very much like our second step, it looks like our tests look very similar. So now we have three tests for our concrete classes, which are Unix socket test, UDP socket test, and TCP socket test. And then we have an IP socket test that shares code between UDP socket test and TCP socket test. And we still have our old socket test, which shares code between all of them. So it's important to have good design in your tests just as it is in your normal code. And that pretty much completes my discussion of the 3 flaws for today, and we're going to get into Q&A. There's a link to my blog, a link to my book, and there's a discount code you can use to get 40% off of the print version and 50% off of the electronic version, and that discount code is AUTHD, A-U-T-H-D. That is my discount code. And if you have questions for me or you want to discuss any of this, there's my email, and I am now open to questions. So I'm going to go look over here at the Q&A section. All right, let's see. First question. Regarding comments, is it better / simpler to comment at the block or paragraph level of code instead of the line / sentence level? So first, let me talk a little bit about what you do want to do and don't want to do with comments. So what you don't want to do in general is explain what the code is doing. Instead, you want to explain why you wrote the code. That is valuable information that's not already there. What the code is doing is information that's already there. So I put my why comments as close to the part of code that will be confusing as possible. You know, at the point where the reader of the code will start to look and think, you know, what's going on with this? Or they might look at it and be like, this is unnecessary, I'm going to remove this. Oh, but no, I'm not going to remove this because there's a comment here explaining why it's there. So that would be my guidance for where comments should go. Question, design patterns, do they tend to help or hinder code simplicity? That's an excellent question. When design patterns are used and they don't need to be used, they hinder code simplicity. The advantage of design patterns is that when you come across a situation where you need to be generic, you have a lot of options that you know about that you could apply to that situation. So I would say that design patterns are valuable as long as you follow, when you're following the sort of incremental development and design practice, or you're following the rule about being only as generic as you need to be right now. But doing the design patterns up front when you don't know if you need them or not can definitely hinder code simplicity. Let's see. The next question is, how do you balance keeping things generic with not making your design rigid? For example, how would you deal with internationalization when at the moment all you support is English? That is an excellent question. Particularly the internationalization question. So ideally what you want to do for that kind of situation is that you want to design a system, let's take the internationalization example. You want to design a system that makes it as easy as possible to internationalize. You know, like the C# system is fairly decent, where you have this XML file and it has a collection of strings, and then you have a class that's automatically generated from that XML file that has properties in it. And so every time you need to put a raw string in your code, you just type it into the XML file, and then you access it as a property on this other object. And that doesn't add a whole lot of complexity up front. It doesn't look too generic, really. But it does make it simpler to do the internationalization. There are a couple of things where there are some things that you want to try to do as early on as possible in the life cycle of your application development, and one of those is internationalization. There are some of these things a couple of these things that you have to know up front that they're going to be so impossible to do later, and you know you're going to, and you know that there's a chance that you might have to do them. You don't know that you're going to have to do them, but there's a fair amount of chance you're going to have to do them. That doesn't necessarily mean that you need to like write in all the code to, you know, have a bunch of different string files that have different localized files, or that you need to write in all the code that like figures out what the user's current locale is. It just means that you want to write it in some way that if you get to a future that requires internationalization, it's fairly easy to deal with. Okay, let's see. Next question. Is the idea overriding too many tests apply to the ideas of code simplicity? Is the idea overriding too many tests? I'm not quite sure on what that question is. Could you clarify that question, and I'll get to it later? Could you just do another Q, and I'll answer it at the end of the list? So the next question is, tips for how to decide what is too generic when writing a framework/external API versus an application. This is an excellent question. The way that I deal with this problem is I always have use cases. For when I have an external API, I do not write it without real use cases from real people. And I'm like, okay, what do you need to do? And I tend to be minimalist until requested, and I try my best to make systems that can be updated rapidly. You're in a better situation if you can update rapidly because you can accommodate those new needs. You need to have developers who have some sort of software management system that allows them to do those rapid updates. The less you can do rapid updates, the more constrained you are, and the more you have to sort of be a little speculatively generic with an external API. Also, external APIs, you do a little bit more checking for types of input, but you can also just write in the documentation like, if you give this bad input, it's going to throw an exception. Don't do it. And you might not even have to say like what kind of exception. You can just say like, if you do this, the behavior is undefined, or so that's not always the best for the user of the API. So sometimes you do want to be explicit about checking. It's really up to you. It's a judgment call, but it should all try to be based around use cases. So the next question is, are there any specific design and requirements methodologies that you recommend, or do you take your inspiration from all of them? Yeah, I would say that I take my inspiration from all of them. I'm not a big fan of any particular fixed methodology. One of the problems of a lot of these fixed methodologies is that they try to combine software management practices with software engineering practices, with software design practices, and you often need to mix and match those for your situation. So I don't think that there's ever going to be like a package of answers that resolves everything. I remember back in the Bugzilla days, people would preach us all of these things about certain ways to develop your application that just didn't work for us because we were shipping a program people would install on their servers. This is a totally different world than most developers live in. A lot of developers live in most developers, maybe even nowadays, live in the world of I write a website and I push this website off as often as I want, and it doesn't require my users. It doesn't, impact my users' maintenance schedules at all if I push the website. But Bugzilla, it's like, oh my God, it's huge. It's a huge deal if we push a new version out. So, there are different practices for different situations. I would study up on all of them and use what's appropriate based on your judgment and based on sort of these rules that we can understand about that are the basis of software design. Question. Dependency injection can hurt readability, but what about unit testing? Even if there's only one real type/object to inject, if I don't have the option of injecting a mock, my test might have to span numerous core modules. Okay. So there's sort of two questions here. I'm going to address the first one about dependency injection. And then there's a sort of implied question that I'm going to address as well. So, yes, I agree that when you do have to inject something in a test, that is a valid other use. That is a valid, there is more than one use. I usually, I personally don't always do, test-driven development, and I don't know any, but I know very few people who actually write their tests first. So I tend to write a small piece of my class and then write the test for that small piece of that class. And so usually I make things generic in my class once I realize that my test needs it, if I see that my tests need it. So I think that is actually a valid case for dependency injection. Although I will have a brief caution here, which is that it's not actually bad to span core modules for the most part in unit tests. And I understand that this is an issue of sort of the school of unit testing, which you believe in. There's a lot of opinions in this area. Although I think a lot of this Yeah, some of this is covered in the book, and it was covered in my previous webcast as well, about how you can sort of make these decisions as to when you should be doing pure unit tests versus when you can be doing or when you should be doing what are called more quote unquote integration tests. And I don't think that these names are actually buying us that much value. I think what really matters is that we have tests, that they tell us that our software works or behaves the way we expect it to, and that they don't pass when they shouldn't pass, that they fail when they should fail, and that they are clear about their failures, and that they run fast enough for our purposes. So I wouldn't knock out everything in your tests because that's also going to add too much complexity to your base code because you're going to have all that dependency injection. Okay, next question. Okay. So is the idea of writing too many unit tests apply to the ideas of code simplicity? For example, providing too many unit tests. Yeah, I think this will be the last, or second to last question. I see one more. So, too many unit tests. You can always write too much code. Like if your tests overlap with each other, like they all test the same things, or then you have too many tests. And less code is better code. And tests have to be maintained just like normal things do. So tests that are not giving you any value, you should get rid of. But you also shouldn't be too speculative about what the value the tests are giving you are. You shouldn't predict, oh, this test is never going to tell me anything, unless it's really, really pretty clear that, like, this test breaks all the time. I have to keep maintaining it, and it's not helping me. So that's when you get rid of it. So I would say that's an area where that applies. And our very last question here is, do you have any thoughts on the size/length of routines and classes vis-a-vis simplicity and complexity? Yes. I think they should be short. Particularly routines. Routines are more obvious. If they get too long, then I just tend to split them up into multiple named routines. One of the values of functions is that they have names, in addition to the fact that they reduce duplication. And so you can take a block of code and you can be like, make a function that has a really long name because you're only using it once. And classes, yeah, the length of classes it can be a problem if you have a really long class. You might want to think about that. But some classes are natively really long. They're just inherently that long. Sometimes I try to split things out into helper classes if I can. That one's less of an issue, but the routine one is definitely something you want to pay attention to. And that is all of my questions. Thank you very much, everybody. And I think Catherine, do you have closing remarks or anything?
Well, I don't have much to say, but I want to thank you for a great webcast today. And it seemed like everyone got a lot out of it. And I also want to thank our audience for all the good questions and discussion that went on. So overall, I would say it was an excellent event. Thank you, Max. And top shelf. Thanks, Rob. And everyone, we will have a recording of this available probably sometime next week. We'll send you an email as soon as it's ready. And I am sorry I neglected to load a copy of the slides into the resource widget, but once you get the recording link, they will be in that resource widget, so you can log in and download a copy of those. No, you won't be obligated to watch the entire webcast again, so I think but you can as many times as you want. So that is about it. That concludes our webcast today. Thank you, everyone, and I hope you'll come back again soon. Thanks, Max. Goodbye.
Thanks. Bye, everybody.